Okay, so we're going to look at your limit laws to start. And a lot of you had questions about how you would go about solving some of the more complicated versions with the limit laws. Well, first of all, you should never work any limit without attempting to substitute in first. A lot of students waste incredible time trying to factor or simplify something that isn't factorable or shouldn't be factored and simplified because you don't have a problem that needs to be factored or simplified. If a problem simply gives you a numerator over denominator answer and you're not dividing by 0, then that is your answer. Notice that my notation has the limit with the x input, it has the function as the output, and it will equal. As long as we still have x terms, we should always still have our limit notation. Once I substitute in the 0, however, I no longer need the limit notation because there's no longer going to be an x in our term. So my final answer is just -1/3, and there is no other simplification or algebra necessary. So you should try that process for these next two problems. For the next part, you're going to be using factoring to solve. The way that I know that I need to factor is if I were to substitute in first, I get 4 minus 12 plus 8 on the numerator, and 2 minus 2 in the denominator. It is only because I answered 0 over 0 that I know that I have to do more work to figure out the answer. So remember, if you get a number in both the numerator and the denominator, that's just your answer. Do make sure that you simplify. If you get a 0 over another number, that's okay. That answer is just 0, and you're done. If you get a number over 0, that's an undefined number. But basically, as far as a limit is concerned, that means that the limit does not exist. And you're done. It's only when you get that 0 over 0, or later on in calculus we're going to see when we get infinity over infinity, that we have to figure out an answer that isn't as obvious. So getting a 0 over 0 automatically means that x equal to 2 is a factor or a solution to both the numerator and the denominator. It's a 0 of both functions. So I'm going to keep my limit notation. I'm going to factor the numerator. And the nice thing is, since x equal to 2 was a 0, I knew that x minus 2 had to be a factor. I can now cancel. Technically, my limit simplified is the limit of x minus 4. And once I substitute in, 2 minus 4 gives me a -2. Try factoring and simplifying for the other parts of question 2. The third method is the conjugate method or rationalization. It also should only be done if you get the 0 over 0. If you don't get 0 over 0, then you should not attempt to rationalize. If you get a number, then that is your answer. If you get 0 on bottom, then the limit does not exist. And if you get a 0 on top, that is still just a number, and you're done. So only when you get 0 over 0. So you really should try to substitute first before spending a lot of time that's wasted for a problem that did not need simplification. So for this problem, if I substitute in the square root of 16 would give me 4 minus 4. 16 minus 16 would give me 0. So that means I do have to do more work. The question is, what work am I going to do? I'm basically going to multiply by a giant number 1. So if I multiply something by 1, I really haven't done anything to change the value. I'm just changing the appearance. So our conjugate, since we have an a minus b, we're going to do an a plus b. So I'm going to do the square root of x plus 4 on the top and bottom. Now an easy way to remember this is that really you're doing a difference of squares. Difference of squares and a conjugate pair are really the same thing. Difference of square, conjugate pair. So if I have an a plus b, I'll use an a minus b, and that's going to give me a squared minus b squared. It's important though to remember that our goal is to multiply by 1 so that we don't change the value. So I have to multiply on the top and the bottom. That means that my limit becomes on the top a difference of squares, and square root of x squared is just x, minus the 4 squared is 16. On the denominator, we never put the non-pair together. So x minus 16 was our goal to cancel. We never put him with the non-friend. So I only put the conjugate pair together. The other part remains unsimplified. That means that we could cancel, and that means the numerator, x minus 16 divided by x minus 16 is 1. Be careful that you don't somehow magically levitate the denominator to the top because he's still on the bottom. Now I can substitute in, and I have 1 on top. The square root is 16 because we're substituting 16 for x, plus 4. So that's 1 over 4 plus 4, so 1/8. I'm going to have you try the other two on your own, but I will work the last one with you. Okay, so first of all, if I substitute in, I get the square root of 2 minus the square root of 2. And if I substitute 0 in, I get 0. So that tells me that I need to use my conjugate rule. So now on the top, in this case, I happen to have a minus b again. So everything that I had initially has to stay. And I'm going to multiply that by a giant number 1, which is a plus b. Notice I'm only changing the signs between the conjugate parts. Notice that I didn't change the plus 2 because this was the a minus b part. So I didn't change a, I only changed the sign preceding the b term. So now, when I work this out, ooh, my handwriting became very, very off right there. Hold 1 second. Try that again. Okay, so we have the limit. The top part is a conjugate pair, so a squared is just x plus 2 minus b squared, which is 2. All over, the non-pair doesn't go together. Notice that I put parentheses on this top part. This is extremely important because it's the entire a term minus the entire b term. It doesn't matter as much on this one because the minus b term is only one term. However, you'll notice in this triad example here that this squared minus the 9 plus x part squared isn't just one term. So you have to remember you're minusing the entire b squared. So be careful with those. So now I have the limit as x approaches 0, x on top, with an x still not distributed because he's not a pair. Now when these x's cancel, it leaves a 1 on top. Now when I substitute in, I no longer need the limit notation. And when I add two like terms together, I just get 2 roots of 2. It's like adding x plus x to get 2x. Okay, the next type that we're going to do is called expansion and simplification. That's a very fancy way of saying that we're looking for a common denominator. Okay, now, I want to remind you that we have to check first. I'm going to get 1/4 minus 1/4, 3 minus 3. Otherwise, again, you could be doing a lot of work that didn't need to be done. Next thing I want to remind you of is that if I divide by the term x minus 3, dividing by a number is really the same thing as multiplying by the reciprocal. So I can split this up to make it a little less confusing so I don't have a complex fraction or fractions on top of other fractions by writing it this way. So the numerator divided by x minus 3 is times 1 over x minus 3. So this part is the only part I really need to find a common denominator for. So I'm going to multiply the first term by 1. I'm just going to write my 1 kind of fancy, 4 over 4. I'm also going to multiply the second term by 1. Just so happens my 1 is going to look like a fancy x plus 1 divided by x plus 1. So now I'm taking the limit of 4 minus this entire fraction. So minusing that entire fraction means that technically this minus 1 belongs with both the x and the 1 here. So really I'm distributing that through because we have a common denominator now. So really the minus 1 is going to distribute. So be very careful about that. And I still have to remember my original denominator that I've moved out to the side. Now in simplifying, 4 minus x minus 1 over 4 times the quantity x plus 1, all being multiplied by 1 over x minus 3. That really now simplifies out to be the limit as x approaches 3 of 3 minus x times the 1 with a common denominator of 4 x plus 1 x minus 3. Now, as a side note, most of us recognize that if we do x plus a divided by x plus a, we'll get 1. X minus a over x minus a is also 1. But x minus a over a minus x has a negative multiplied here is negative 1, and vice versa. So on the one that we have, 3 minus x and x minus 3 do cancel, but they don't make 1 on top. They make negative 1. Now, when I substitute in, I have to substitute into negative 1 over 4 times the quantity x plus 1. So negative 1 over 4 times, now when I substitute the 3 in, I get 3 plus 1, which is 4. So my answer is negative 1 over 16. You may want to pause the video and rewind to watch that again before trying this problem. Now, we talked about what happens if we get a number over a number, and 0 over a number, and even 0 over 0. But what happens when we divide by 0? Technically that means the limit does not exist, but if you want to know the sides of the limit to see where they're going, then in order to graph, you could figure out what was happening prior to that. So in order to do that, I would consider, because we are going to get, in this particular case, 9 divided by 0, so I know the limit does not exist. But if I let x be approximately 1.9, I can consider that the left-hand side of x. All I care about is whether or not the limit would be positive infinity or negative infinity. Because it's a vertical asymptote, I already know that it's definitely one of the infinities and the limit does not exist. So if I'm slightly left, I know that the numerator would be 2 times 1.9 plus 5 over 1.9 minus 2. I don't even care what that is exactly. I only care that it's a positive over a negative, so a negative overall. That means that the limit from the left-hand side is negative infinity. If I were to let x be approximately even 2.0001, so just barely to the right of 2, I know that the numerator is going to be a positive number. I know that 2.0001 minus 2 is still going to be ever so slightly positive. So that tells me I'm going to have a positive infinity. This also tells me that since these two limits don't match, I can't even say that both sides are going in the same direction. So the two-sided limit has only one choice. The limit does not exist. Let's try that with another problem. If we were to use, let's say the last one, negative 3. So let's let x about negative 3.1. I'm going to have approximately positive 9, but because it's 3.1, this will be slightly larger than positive 9. So it's going to be positive 9, but a little bit bigger, and then a negative 6.2, and a negative 3. But this 0.1 squared, 0.1 times 0.1, is going to end up being what type of value? So if you're not sure, you can do 3.1 times 3.1. But notice what happens. 9.61, so we go into the hundredths place. So 9.61 minus 6.2 minus 3 is actually a positive number. On the other side, I have 9.61 again, minus 18.6 plus 9. Well, the 9.61 and the 9 are slightly more positive than the negative 18.6. So I am going to end up with a positive over a positive. But that's the left-hand side. What about the right-hand side? Another way to think of this is to think about your factors. If I factored the numerator and factored the denominator, I wouldn't need a calculator. X, 3 and 1, positive 3 and negative 1, x plus 3, x plus 3. First off, I can cancel out, but even if I couldn't cancel, this is much easier now to consider. If I look at this now, the negative 3.1 would be a negative over a negative, which is a positive. If I do the right-hand side, and remember this is negative 3, so just to the right of negative 3 would be like negative 2.9. So if I substitute that in, the numerator is negative, but negative 2.9 into the denominator is positive, so that's a negative infinity answer. So again, this side does something different on the left and the right. So I know the limit as x approaches negative 3 from both sides simply does not exist. Notice for this question, 4 over x squared, 4 is always positive, x squared is always positive. That tells me that all sides, anywhere that x is not 0, everywhere, that this has to be a positive function. That means that I know both sides of this function do the exact same thing, meaning they both go to positive infinity. So my two-sided limit could be infinity, or I could choose to say that the two-sided limit does not exist. Now remember, technically the limit does not exist anytime you get a vertical asymptote. So I'm going to leave this one for you to try. Okay, for our piecewise equations, we really don't have to graph them in order to know how to do this. This is simply asking, do the two sides equal each other? X greater than 1, if we think about the number line where x would equal 1, x greater than 1 is the right-hand side, less than 1 is the left-hand side. So this is my left, my right, and because the equals is here, this is going to be the dot. Remember, for the limit, we actually don't need the function value. We only need what the function is approaching from each side. So the limit as x approaches 1 from the right of f of x could also be written by substituting for f of x, and just the f of x part you could put x squared minus 4. But notice once I put the 1 value in, 1 squared minus 4 does not have limit notation because there's no x to approach. And so the y value is approaching negative 3. The limit as x approaches 1 from the left of f of x. I can substitute in negative 2x minus 1. And 1 from the left is negative 2 minus 1 is also negative 3. So since the left and the right are equal, the two-sided limit as x approaches 1, y approaches negative 3 from both sides. Okay, I'm leaving the next one for you to try. Okay, finally, we're going to find values that actually make a limit exist. If we want to find the value of the constant k such that the two-sided limit is equal to the function value, notice that for x not equal to 2, that is both sides of 2. That's basically saying everything except 2, we're going to give you a value. And then the value for 2 could be something else, a different dot. So this is really just the dot, where this part's the left and the right. Now, that means that we can skip in this doing the left separate from the right and simply say that our two sides of x equals 2, or x approaches 2, both use x squared minus 2x minus 3. That means that we can simply substitute in, since there's no denominator, and get 4 minus 3, which is negative 3. Our function value is only the dot where x is actually equal to 2. Notice that there's no x term here. A lot of people accidentally substitute into k. So the function value at 2 is just k minus 3. So if our goal is to have the two-sided limit equal to f of 2, that means that negative 3 has to equal k minus 3. Now if I add 3 to both sides, I'll figure out that 0 has to equal k. For this next one, I'm going to do the same idea, the two-sided limit equal to the function value. Notice again that my left and right of 7 are both the top part of the piecewise function, and the bottom part of the piecewise function is just the dot. That means that for both sides of 7, I can simply find the limit of x squared minus 49 over x minus 7. You should notice that we end up with a lot of questions that are difference of squares. College Board loves difference of squares. So you're going to see that frequently as something you should know. That and the conjugate pair, because remember, a conjugate pair is also a difference of squares. Now this time when we canceled the denominators, what went away, and we have a 1. But now we can substitute in. Now that there's no denominator except 1, when we substitute in, we get 7 plus 7 over 1, so just 14. Now the function value at 2 is this bottom piece, and that's k squared minus 2, not x squared. Notice that my function notation here never has an x value in it. Even when we were doing other parts, when we were doing a function value, once we substitute in, so if I were doing f of 2, f of 2 is defined using this piece, which would be 2 over 0. That function is undefined at x equals 2. Notice that there's never an x value in this part, so there's never an x value in this part. When we have limits, limits are limits of functions, so we don't do limits of constants the same way unless the function itself was always a constant. So f of 2 equals k squared minus 2. We're now going to set our limit equal to the function value, because the question asks us what value of k would the two-sided limit equal the function value. So we have 14 equal to k squared minus 2. If we add 2 to both sides, we get 16 equals k squared. So k has two answers, plus and minus 4. You would have to include both in a question to get full credit. So hopefully you can use this information and these examples to work through the sheet on this page. I did give you some information about how to factor the sum and difference of cubes. You will need to know some of your trig values from pre-calculus. Remember your difference of squares. And that a conjugate pair is just the difference of squares. So from a conjugate pair, you would end up backwards at a squared minus b squared. Remember that a squared plus b squared is not factorable, unlike a cubed plus b cubed, which is. Okay, good luck.